Let's say you're trying to figure out how fast a car is going at an exact moment. Not over a minute, not over a second, right now. You can't just divide distance by time because the time is 0. So how do you define speed at a single instant? That's where limits come in. Or maybe you want to know the area under a curve. You can't just add up an infinite number of rectangles, but calculus can. And the tool that makes both of these ideas possible is the limit. A limit is what a function is getting close to as the input gets close to some number. Not necessarily what it equals at that number, just what it's approaching. For example, take the function f of x equals x squared. If you plug in values near 3, like 2.9, 2.99, 3.01, you'll see that f of x gets really close to 9. So we say the limit of x squared as x approaches 3 is 9. Written as lim x approaches 3 of x squared equals 9. Now, here's the key idea. We care about what happens near x equals 3, not necessarily at x equals 3. The function doesn't even have to be defined at that point. Imagine walking toward a door. You can get as close as you want without touching it. That's what a limit is, the value you're getting close to. Let's look at a more interesting example. Suppose f of x equals x squared minus 1 over x minus 1. If you plug in x equals 1, you get 0 over 0. That's indeterminate. But if you factor the top, you get x minus 1 times x plus 1 over x minus 1. Cancel the x minus 1s, and you're left with f of x equals x plus 1 as long as x isn't 1. So as x approaches 1, f of x approaches 2. The limit exists even though the function isn't defined at x equals 1. Now try this one. F of x equals 0 if x is less than 0, and 1 if x is greater than or equal to 0. As x approaches 0 from the left, f of x is 0. From the right, it's 1. The left and right limits don't match, so the overall limit doesn't exist. This is called a jump discontinuity. So why do we need limits? Because plugging in doesn't always work. Sometimes you get undefined values like 0 over 0. Sometimes the function has a hole. Sometimes it jumps. Sometimes it goes to infinity. And sometimes it oscillates wildly, like sine of 1 over x near 0. Limits let us describe what's happening near a point, even when the function itself is misbehaving. And limits aren't just a side topic. They're the foundation of calculus. Take continuity. A function is continuous at a point if 3 things are true. The function is defined there, the limit exists, and the limit equals the function's value. No holes, no jumps. Now take derivatives. The derivative is the limit of the average rate of change as the interval shrinks to 0. For example, the derivative of x squared at x equals a is the limit as h approaches 0 of a plus h squared minus a squared over h. That simplifies to 2a. So the slope of the curve at any point is 2 times the x value. That's a limit. Integrals? Same idea. The area under a curve is the limit of a sum of rectangles as the number of rectangles goes to infinity and their width goes to 0. That's how we calculate total distance, total area, total anything that accumulates. Now, let's clear up a few common misconceptions. First, the limit doesn't have to equal the function's value. Second, if you get 0 over 0, that doesn't mean the limit doesn't exist. It means you need to simplify. Third, a limit is a process that gives you a value. And fourth, a function can have a limit even if it's not continuous. So how do you actually compute limits? If the function is continuous, just plug in. If you get 0 over 0, try factoring or simplifying. If there's a square root, try multiplying by the conjugate. If it's still indeterminate, use L'Hopital's rule. Take the derivative of the top and the bottom and try again. If the function is trapped between 2 others that both approach the same value, use the squeeze theorem. And if all else fails, use a table or a graph to estimate. Here's a classic example. Lim x approaches 0 of sine x over x. You can't plug in 0, you get 0 over 0. But using the squeeze theorem or a known identity, you find the limit is 1. This is one of the most important limits in calculus. Now let's talk about infinity. Limits let us describe what happens as x goes to infinity. For example, lim x approaches infinity of 1 over x is 0. That's how we define horizontal asymptotes. Or you can have limits that go to infinity, like lim x approaches 0 from the right of 1 over x. That's a vertical asymptote. Infinity isn't a number, it's a direction. Limits let us talk about it precisely. There's also a formal definition of a limit using epsilon and delta. It says, for every epsilon greater than 0, there exists delta greater than 0, such that if x is within delta of a, then f of x is within epsilon of L. That's how you make getting close mathematically rigorous. So why do limits matter in the real world? Because they let us define instantaneous velocity in physics. They let us define marginal cost in economics. They let us model growth rates in biology. They let engineers analyze stability and signal behavior. They let us calculate probabilities from density functions. Limits are the microscope of math. They let us zoom in infinitely close to understand what's happening at a single point or over an infinite process. To sum it all up, limits describe the value a function approaches as inputs get close to something, and they're important because they provide the rigorous foundation for continuity, derivatives, and integrals, the core ideas of calculus.